back?
I don't know.
I got one more for him.
Oh,
This
shoot.
is one of your parents.
Hi, everybody. I think we're back. There we are. Oh. All right, got my calculator pulled up now. All right, so again, this is section 6.6, day 1. We're going to do section 6.6, day 2 tomorrow. So the first thing that I want to talk about is just a kind of a recap. Now, you don't necessarily need to write these down, but this is just a recap of everything that we've learned thus far about roots of polynomials. And this does go back to thinking about roots of quadratics as well. We started way back, I think it was in chapter 4 or something. No, sooner than that probably. When we talked about quadratics, talking about roots of a quadratic. Okay, roots of a quadratic. Those are the places where it crossed the x-axis. If it even did cross the x-axis. They were the x-intercepts, if they had them. R is an x-intercept of the graph of P of x. We would know that if I plugged that root in, you get out 0, which means that it's an x-intercept anyway, right? If you have the x value of r, where r is a root, you must get out 0 if it is truly a root, which also ties into the fact that if we divide P of x by x minus r, doing synthetic division, you should always get a 0 in as your remainder. A real number r is the root of the polynomial equation. P of x is equal to 0. We talked about P of r is equal to 0. It's an x-intercept. It's a factor of P of x, right? We know that x minus r is always going to be a factor. Every root will have a corresponding factor associated with it. We'll talk about it a little bit more today. When we divide, we get a remainder of 0, and we can call it a 0 as well. So we know all of these things about roots of the equation now, right? This is kind of why we've been talking about factoring and finding the roots and division, because it all ties into finding the x-intercepts and finding the roots of an equation, okay? We did this sort of process. We did this process this similar way with quadratics. Remember back in quadratics, I said, okay, we were given the equation and I asked you to find the roots, right? Now what we're going to do is I'm going to give you the roots and ask you to find the quadratic. We're going to do that same thing, but now I have 3 roots. I not only have just 2 roots, but I have 3 roots because now we're talking about polynomials. So let's start here, right? The simplest polynomial with the given roots. I've got -2, +2, and +4. So what does that mean? I need to figure out the factors, because once I figure out the factors, I can multiply the factors together to find the polynomial. So we're going to work ourselves backwards. We've got x equals -2, we've got x equals +2, and we've got x equals +4. We all follow me there? Those are my 3 roots to this equation. So what are my corresponding factors to these roots? Well, if I add the 2 over to the other side, I get x plus 2 equals 0. If I subtract the 2, I get x minus 2 equals 0. And if I subtract the 4, I get x minus 4 is equal to 0. So the polynomial can be represented like this. Here's f of x. I've got x plus 2. I've got x minus 2. And I've got x minus 4. So there's my polynomial, but can I leave it like that? No, I got to FOIL it out. We've got to multiply this entire thing out. So let's do that. I noticed that this is a difference of squares, so I'm going to multiply those 2 things together first. So f of x is going to be equal to, we've got x squared, my firsts are x squared, my outers and inners are both positive 2x and negative 2x, so they will cancel out. And then we get a minus 4. And then we multiply with just a plain old x minus 4. Everybody follow me there? FOIL this out. My firsts is x to the 3rd. My outer is minus 4x squared. My inner is minus 4x. And my last is plus 16. So that's the simplest polynomial with those factors. Can I let you in on a little secret? This is how we make your tests. Like when I want to give you a problem and ask you to find the roots of the problem, you know what we start with? We start with the zeros. And when we basically do this exact same thing until we get to a polynomial that you guys have to solve. That's basically what we do to create those problems where I say to find the zeros. Let's try another one. Do this one along with me. I've got x equals 0, x equals 2/3, and x equals 3. fraction. We're talking about fractions. We're not talking about whole numbers. We're talking about fractions. All right, we've got x equals 0. X equals 2/3. And x equals 3. I don't know about you guys, but that fraction, I don't like that fraction. So let's do something with it. Can anybody tell me the corresponding factor that would go along with that root? What would I do with that 3 first? 3's on the denominator, so what should I do to bring it back over? I'd multiply it, right? So we got x equals 0, we get 3x equals 2, and then what would I do with the 2? Subtract it back on over. So 3x minus 2, that's the corresponding factor that goes along with that root. I would caution you against trying to use the fraction. Okay, that happens a lot when we get to the test or quiz. I think it's the quiz, and there's a fraction on there. I want you to use like this 3x minus 2. I don't want you to try to use x minus 2/3. By all means, if you'd like to, you can, and it would not be wrong. But please, please, please don't do that, because then you get a whole bunch of messy fractions. And then we've got x minus 3. Okay, so I've got x 3x minus 2, and x minus 3. Okay, let's distribute in the x to the 3x minus 2 first. 3x squared minus 2x. And then we'll just FOIL this out. And you know what? I can leave off the equals 0, because now we're looking at the full polynomial. Let's call it f of x. Now let's FOIL it out. My first 3x squared times x is a 3x to the third. My outer is a minus 9x squared. My inner is a minus 2x squared. My last is a plus 6x. Combine like terms in the middle, and I get 3x to the third minus 11x squared plus 6x. And that's it. Now we can see where this is going. Tomorrow what we'll work with is, are all roots always rational? Like these ones? Are all roots always rational? No, we saw that with this volume of the box problem that I still have on the board, right? One came out to be a non-real solution. So what do we do then, right? How do we put it back together then? What happens if it's irrational? What happens if it's non-real? We'll spend tomorrow talking about that. Okay. Okay, get ready for it. Here it is. The fundamental theorem of algebra. I feel like there should be like an echo with my voice. The fundamental theorem of algebra. All right. We've almost kind of talked about it a little bit already, and maybe some of you guys have picked up on it. Guys, how many roots did I start with on this very first problem that we did? We started with 3, right? Negative 2, positive 2, and 4. What was my power on the final polynomial? 3. How many roots did I start with here? What was my final power?
3.
Okay. Let's jump back to our homework key. Now take a look here. Take a look at problem number 4. How many roots does it look like I had? 2, right? However, didn't we have multiplicities? How many times did x plus 4 show up? Twice, right? So we had 2 x equals negative 4s and 1 x equals negative 2. What was my final power? 3 altogether. Think about number 6 here. Look at the power. X to the 4th, right? Look how many zeros I've got. 1, 2, 3, 4. Take a look here. X to the 4th. 1, 2, 3, 4. So basically the fundamental theorem of algebra states that you will always have every polynomial function degree of n greater than or equal to 1 has at least one 0, where 0 may be complex. This is the good stuff there. Every polynomial function of degree n greater than or equal to 1 has exactly n zeros. I mean, it's, again, fundamental. Okay, well, that's a cool theorem. I mean, but fundamental? I don't know. It just basically says that every polynomial, no matter what, as long as it has a degree of greater than or equal to 1, binomial. That'd be a tricycle.
No, you're in the fact you guys have a wheel on.
No, that'd be a tricycle.
No, we're gonna just like drag a Lego wheel off the back.
No, that'd be a tricycle. All right, every polynomial function has exactly n zeros, where n is the degree. Okay? The only tricky part here is that you just have to include multiplicities. You've got to include multiplicities. Okay?
Training wheels if you call it quads.
A quadsicle?
Because I mean,
A creamsicle?
because by your logic, if I have training wheels on my bike, it's not a bicycle.
Yeah, that's true. If you've got training wheels, it's not technically a bicycle.
It's
You use those training wheels on your bike?
You never know.
Okay.
Training wheels for you, so-
Let's jump to an example.
It'd be a tricycle. I know, that's what I was asking.
Guys, I'll tell you what, from this point on in today's lesson, we're doing the exact same thing as we had done before. Sorry, did anybody study that? Yeah, I'm sorry, I'm getting a little excited.
Unbelievable.
Getting a little excited, sorry. Talking about quadcicles and then thrown off. Sorry. Now, what are we gonna use with this? Well, I mean, we're not really gonna use this at all. It's just like an important piece of information that we need to know. Okay? It's one of those things where you have to go back and check in the end, like, okay, I started with an x to the 5th. Am I sure that I have 5 zeros? Or I started with an x to the 3rd. Am I sure that I have 3 zeros? This includes all irrational and complex roots as well. And don't forget that when you write a plus or minus, that is 2 different roots. 2 different roots.
Wait.
A multi-seat bike.
The sidecar? Four-seater bike. So like a motorcycle has a sidecar. What?
I would call that a tricycle.
What
Because the
about
sidecar has only one wheel, right?
wait. What about those tires ones that have like 2 wheels in the front, 1 wheel in the back, like the big, massive, chunky ones?
Yeah, those
Tricycle.
are tricycles.
Tricycle. So reverse.
By definition,
Trimobile.
it's a tricycle.
Trimobile.
What's that?
Trimobile.
The car one?
The car is a quadcycle.
No.
I think quad
Yeah, I mean, by definition, right?
Debate on the
This
wheel.
conversation brings me pain.
Why are we having a debate on the wheel?
All right, take a look here. Did anybody study that? Hopefully we're good.
Oh my God.
So, how many roots should I see at the end? I should see 4 roots, and including multiplicities, right? See, that's what the fundamental theorem of algebra tells us. Now I just have to solve it. I'll let you in on a piece of information that you're going to want to know here. This quiz on Monday is going to be full calculator. Okay? It's going to be full calculator. You are not, that means that you're not going to have to do the P over Q on this quiz on Monday. However, there will be a portion of your test when we get to the chapter 6 test, and there will be a portion of the group test that will be a no calculator portion. Okay? So you will have to do the P over Q thing later. But I'm just telling you right now, this quiz on Monday is full calculator. So you will be able to use your graphic calculator. What does that mean in terms of this problem? Can I factor this as it sits right now? I can't factor it right now. So what do? If I have my graphic calculator, we graph. So let's do that. So I go into my y equals, and I say x to the 4th minus 3x to the 3rd plus 5. X squared minus 27x minus 36. Okay, I see a straight through and a straight through. Now, How many roots do I see on my graph? 2. Do any of them have extra multiplicities? No, they don't. So that means that there are unreal roots going, or non-real roots going on, right? I see 2 roots on my graph, 2 places where it's going straight through. So there are actually non-real roots because I know I'm going to have a degree of 4, right? Okay, so where do they look like they exist? One looks like a -1, so let's test it out. Let's test a -1. I got a 1, a -3, a 5, a -27, and a -36. So this gets me a 1, a -1, a -4, a +4, a 9, a -9, a -36, a +36, and a 0. Really?
Oh yeah.
That was insane.
Numbers came out of
That was?
there. And they
Man, if you're impressed by that, just wait till we get to later on in the year. Got some extra. I've got more skills than that. Come on now. Yeah. You know, Texas Instruments contacted me about going pro, but I was like, you know what? I'm here for the kids. I'm not here for the money. I'm here for the kids.
Stick to
Okay?
my roots.
There's one message in every
Says Lambert on the back. Sponsors Ticonderoga.
Yeah, really. When I turn around and you see patches on my back of like all the, sponsored by.
Got a YouTube sponsor.
Yeah.
I'd buy that jersey.
All right. Now, what should we check next? We should always check to see if I can. Ooh, can I factor this? I can factor this. What?
Where?
What? Look at that. I can factor this by grouping. So I've got x plus 1. Now, could I have gone through and synthetically divided out a +4? Of course. But watch what's going to happen. I can factor this to get an x squared, to get an x minus 4, and then a 9 to get an x minus 4. So that means I've got an x plus 1, x squared plus 9, x minus 4, which I see the x minus 4 now. That root is going to show me the x equals 4. But there's one thing left over. The x squared plus 9. I've got an x equals -1, an x equals +4, and then this x squared plus 9 equals 0. Because it's down to a quadratic, life is good, I can do the quadratic formula. Oh wait, there's no b term, just solve directly. X squared is equal to -9, x is equal to plus or minus what? 3i. So, do I see 4 roots? I only boxed 3 things, but do I see 4 roots? Yes. 1, 2, 3, 4.
Wait, I don't.
Why?
The plus or minus.
Oh.
That's 2. Yeah.
Get some every time. Life.
Let's try this last one here. Sorry, did I go too fast for anybody? Did anybody still need that last one?
Gotta be
Little-
high.
Did anybody still need the word for the last one?
I'm good.
Just the answer. Just,
I'm gonna break the plan.
there you go.
See, there's one.
Actually,
Yeah, it's broken.
when they are prove this theorem.
Things are not going to be broken.
One day.
You spin your one.
Okay, here we go. Got 2x to the 5th plus 16x to the 4th plus 36x cubed minus 54x. What's the first thing that you should always do? Check for a GCF, and I do have a GCF in this case. It's a 2x. Leaving us an x to the 4th plus 8x cubed plus 18x squared minus 27. You should check now to see if it factors, but guess what? It does not.
Calculus.
So, yes. No, I pulled out the x.
Oh, yeah.
So now we go into our y equals, and we chip away x to the 4th plus 8x cubed plus 18x squared minus 27. I see a bend and a straight through. I see a bend and a straight through. Right, I see a bend and a straight through. So looks like it's at -3 and +1. Which one do you guys want to do now? +1? I heard a +1. Got a 1, an 8, an 18. Don't forget about my 0 as a placeholder for my x term. Drop down the 1. 1, 9, 9, 27, 27, 27, 27, and a 0. So we've got a 2x, an x minus 1, x cubed plus 9x squared plus 27x plus 27. And now I can use my -3. We saw a bend through at -3, so I know there's at least 3 roots there. With a 1, a 9, a 27, and a 27, which gets me that. So we have a 2x, an x minus 1, x squared plus 6x plus 9. So what I can do now is factor that last quadratic. Now, if I wanted to, if you didn't see that it factored, could you do the quadratic formula? Of course, but guess what? It would just give you 2x plus 3's. So we got 2x. Oh, I forgot an x plus 3 from this one.
Oh,
Sorry.
this one's after 8.
So we get, x, it's not a mess up if I sound proud of myself. X plus 3, x plus 3, x plus 3. So we've got an x equals 0, an x equals 1, and an x equals -3. It looks like I only have 3 roots. But in essence, but in reality, I have 1, 2, 3, 4, 5 roots. Right? Because the -3 has a multiplicity of 3. I really see all 5 roots. Here's 1, here's 2, here's 3, 4, 5. That make sense? Okay. Hope we all have a good day. So long for the folks. Hold on, I'll go back. Don't worry, I'll go back. I just got to turn off. So long, everybody.